You got it right here, man. You're right here. Squeeze it right here.
Are there any questions? Or are there any questions? Okay, if you remember at the end of the last hour, we had an equation that looked like this. If I can find it. Well, if you remember, we were assuming a single stoichiometric reaction. Alpha 1, A1 is alpha 2, A2. Goes reversibly to beta 1, A1 plus beta 2, A2 plus dot, dot, dot. I put this on the blackboard just so we recall what the alphas and the betas are, the stoichiometric coefficients. And we came up with an expression that said minus the sum on I, beta I minus alpha I, phi I of t, where we had an expression for phi I of t that involved a whole bunch of terms from statistical mechanics that clearly only depended on temperature. It was equal to the sum on I, beta I minus alpha I, log, let's see, I wrote it that way, log CI equilibrium plus the sum on I, beta I minus alpha I, times log RT. Okay, so, and then what we did is we noted, we defined A, the absolute activity, of species I. As e to the minus phi I of t. Again, phi I of t was well defined last time. And as a result, this is equivalent to saying that phi I of t is equal to minus log ai of t. So that says we can plug into here, and we have the sum on I, beta I minus alpha I. Whenever I see a minus phi I, minus here, I can write log ai of t. And we noted that we could rewrite this as the sum on I, beta I log ai of t. Actually, why don't I write a little further over? Minus the sum on I, alpha I log ai of t. And this we could write as the sum on I, log of ai of t, beta I, minus the sum on I. Well, there's really no big reason to write it that way. Beta I minus alpha I. There's no reason to break it up this way. And the log of, the sum of the logs is the log of the product. So this is the log of the product, ai of t, to the beta I, over the product on I. Here I've changed from I to j because I want you to do this product once and then this product once, and not to combine them. aj of t, the alpha j. And we can notice what this thing looks like. This is just equal to a1 to the, this is the log of a1 to the beta 1, a2 to the beta 2, dot, 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 divided by a1 to the alpha 1, a2 to the alpha 2, dot, dot, dot. And this should look like what you're used to seeing from freshman chemistry, or even high school chemistry. It's the product of the activities raised to the stoichiometric coefficients on the right, divided by the product of the activities raised to stoichiometric coefficients, respective stoichiometric coefficients on the left, which is what we generally call the true equilibrium constant. Here I'm writing it as K with a little a, so you know that it's written in terms of the activities, Ka of t. And the important thing is that we know that the equilibrium constant is only a function of temperature because it comes from these activities that only depend on temperature. And the activities come from the phi's that only depend on temperature, and we would write out the phi's explicitly. Okay, so the left-hand side of the equation is the log of the equilibrium constant. And now for the right side of the equation, we can notice that this has exactly the same form that this had. It's exactly the sum beta I minus alpha I log AI log CI equilibrium. The only difference is here I had AI's, here I have CI equilibrium. So on the right side of the equation, I can see that this, by the exact same algebra, is the log of Kc, where, that is, I will conform an equilibrium, something that looks like an equilibrium constant, but instead of AI's, I've got CI equilibriums. But I get the exact same algebra, it's the same for this. And similarly, this is, well, this one is not so similar, this one's even easier, because I've got the sum of beta I minus alpha I log RT, and log RT has nothing to do with I, so this comes out of the sum. And then I just have the sum of the stoichiometric coefficient on the right minus the stoichiometric coefficients on the left, which is just delta n. So this is just RT log delta n. Or, so what I have here is I have the log, and this thing is equal to the log of Ka, of P. Where I write, I break my jaw. And I write K of t, I write the t dependence, make that explicit, because to emphasize that this is only a function of t, not anything else. Okay, so if I just take the exponentials of this, I have that Ka of t is equal to RT to the delta n to the RT. I think I have it the other way around. This should be delta n log RT. I pull this out, and this is just delta n. So here I have RT to the delta n, K C. So here's the first relationship between a true equilibrium constant that depends only on temperature and the equilibrium constant that we usually work with, which is written in terms of the equilibrium concentration. Now, we probably want to write this in terms of some other things as well. So let's notice, for example, that the concentration, CI, can be written in terms of partial pressures. So let's start with the ideal gas law. Remember, we've assumed ideal gases. So the ideal gas law is PV is equal to N RT. And if I, and let's write this as Ni. I'm sorry, let's write this as N. If I write this with partial pressures, I have PIV is Ni RT, where PI, no. So let's note that Ni over V, CI, is Ni over V, is equal to PI over RT. So immediately, wherever I see a CI, I can replace the CI's by PI over RT. So log of CI equilibrium is equal to log of PI equilibrium over RT, which is the log of PI equilibrium minus the log of RT. And since I have a sum of beta I minus alpha I times this, so I have the sum of beta I minus alpha I PI log PI equilibrium plus the sum of beta I minus alpha I minus the sum of beta I minus alpha I log RT. So Kc, log of Kc, is the log of Kp, written in terms of pressures, and then I have a minus. So then I subtract off minus RT to the delta N. So if we did this correctly, this looks like it should be Kp log, just Kp. Is that correct? That looks okay. Okay, now let's also look at, let's also notice that Ci, as we said, is Ni over V. And let's note that Ci, which is Ni over V, is equal to Ni over N total times N total over V, where this is the mole fraction, Xi. So this is Xi times N over V, total N over V. So again, I could note that log Ci is equal to the log Xi plus the log N over V. And therefore, this can be written as Kx, K written in terms of x's, times, and I have an N over V. Again, just as I had there, so I have an N over V to the delta N. So here I have a bunch of relations. And I could also notice that N over V, I called it little n. Little n over V is P over RT. But that doesn't really help because that doesn't really change anything. I've decided to do things in terms of n, in terms of v, but I can write that that's equal to kx times P over RT to the delta. So we have all these little relations here. Any questions on how to get those relations? Okay, so it would behoove us to look at a particular relation, the Van Hof's equation, which tells us how the Helmholtz free energy changes with the number of moles. And that's written in terms of the heat of reaction. So I'd like to define the heat of reaction. Enthalpy, not the Helmholtz free energy. Now the heat of reaction is something that you see in even in high school. You have it on the regions, certainly in freshman chemistry. And what's the main utility in terms of when you're a freshman doing freshman chemistry of knowing the heat of reaction? That's a question.
You have reference statements?
You can know whether the reaction's endothermic or exothermic.
Depending on the sign of the heat of reaction, you know whether the reaction's endothermic or exothermic. And it's also, of course, useful in a heat balance because you know how much heat is actually either absorbed or evolved upon reaction. So Van Hof's equation says the heat of reaction, says dH dN is equal to, and let's get this right, at constant T. That's the definition of the heat of reaction. And Van Hof's equation, and well, before I get to Van Hof's equation, that'll come afterwards, this is equal to minus T ddt of delta G at constant pressure and NJ. And Van Hoff's equation tells me that RT squared ddt of log of the equilibrium constant is equal to delta H is equal to the heat of reaction. But before I do that, I'd like to continue with this, because we had an expression for delta G. If you remember, delta G, so this is minus T ddt. Delta G, we said, was equal to the sum of beta I minus alpha I times mu I at equilibrium. And this is, of course, at equilibrium. Okay, and what is the heat of reaction in words before I actually take that derivative? The heat of reaction in words is the heat absorbed per unit reaction in the vicinity of equilibrium. So this is defined as the heat absorbed per unit reaction close to equilibrium. Yes?
Delta K is KE, right?
Yes. Okay, and I have to remind you, in order to take this derivative, I have to remind you what mu I was. So I'm going to get back to this because I'm actually going to derive this equation, Van Hoff's equation. But let me just remind you what the mu I was. Mu I is equal to RT times phi I of t plus the log of Pj. So let's see what happens when I take T ddt of this, P and J at equilibrium. So when I take the derivative, I've got two factors that depend on T. I've got this factor and this factor. So if I take, so I have a product of two factors of T. I take the derivative of this factor, I lose a T. When I multiply by T, I get this thing back. So I have delta HR is equal to minus well, I just get this back, so I have minus sigma I to beta I minus alpha I, mu I, P and J at equilibrium. And then I have another term, which is minus T ddt. So I have a minus RT squared, with T times this, with the minus sign. And then I've got a ddt of this thing. So I've got ddt of the sum in I, beta I minus alpha I, times phi I of t plus the log of pi. And this again is done at P and J equilibrium. Okay, so the first thing to notice before I turn to this term is, by definition at equilibrium, what do we know? This thing is in fact nothing more than delta G. That's sigma bi, beta I minus alpha I, mu I. What do we know about delta G at equilibrium? It's 0. So this term is identically 0. And now all we have is the second term.
So if UI is just a function of temperature, why do you do the function?
Because I also have, if phi is only a function of temperature, but pi is not just a function of temperature. Pi can depend on other things. Pi does depend on other things. And actually, if I look at the formula, it actually because pi depends on other things, but this actually is a capital ddt. My mistake. Okay, but since I'm keeping capital P and NJ fixed, since I'm keeping those fixed, then log PI does not depend on temperature because I'm keeping this fixed. So this goes out. And this thing, what's left, is just KA of T. So as a result, what we've found is that delta H is minus RT squared ddt of log Ka, which was the equation I had up here before that we called Van Hoff's equation. So I have ddt of log Ka of T is equal to 1 over RT squared times delta H R. And I seem to have an extra minus sign. Oh no, I don't have an extra minus sign because the minus sign was part of the log Ka. Remember log Ka was minus sigma beta I minus alpha I phi f. So this, together with this, gives me the Ka, and I have plus delta H over RT squared. So let's integrate this equation. In principle, the heat of reaction, yes? Can you please speak up so I can hear you? The derivative of delta G, I'm sorry? No, delta G, the definition of equilibrium is of a reaction is when delta G is 0. So that says that there's no gain or loss in, I'm sorry, yes, when delta G is 0. But the reaction does not change delta G. Does not change G. Okay, so the heat of reaction may in principle be a function of temperature. So I can integrate this to get log A of T is equal to delta H R of t over R t squared integral dt prime from some reference state. So I need to integrate this over Ka of t0 to t. So if I know Ka at any one temperature, I can get Ka at another temperature by integrating this, as long as I know the heat of reaction as a function of temperature. Now, what's the typical form of delta HR as a function of T? How do I know that? Well, delta HR is the reaction at one temperature, say at T, T2, is related to the heat of reaction at T1 by the specific heats. So this is the sum of beta I minus alpha I CPI is T. And I have to integrate this from T1 to T2 dt. So how do I change the heat? How does the heat of reaction change when I go from one temperature to another? Well, in order, the heat of reaction changes by virtue of the fact that each of the species, the specific heat of each of the species changes, is different from one temperature to another. So when I have a certain amount of heat released by the reaction, some of that heat can get absorbed or emitted from the species. It can get eaten up by the species. So it's related this way. So if I plug in here, then I have log Ka of T over Ka of T0 is equal to the integral of delta H 1 over RT squared. And we call this T0. And now for delta HR, I have sum on I, so this is dt prime. And here I have a sum on I, beta I minus alpha I. Times the integral, say from T0 to T prime, CPI of T double prime, dt double prime. So here I plug in for delta HR of T prime, and this should be T prime. Now, often we can neglect the difference. Often this particular term is quite small. If the reactants and the products have similar CPs, then this term is generally not going to be very significant. So if delta HR is only a weak function of temperature, then we can do this, then we can take delta HR out of the integral and do the integration. So then I have that the log of Ka of T over Ka of T0 is the integral of 1 over RT squared, which is just minus 1 over T. It's just 1 over R times minus 1 over T. So it's 1 over T0 minus 1 over T. An R here. And this is particularly useful. Delta HR is often a weak function of temperature. So as long as there aren't big differences in temperature between where I know K and where I want to apply K, then I can often apply this and I can see how things vary.
Isn't there supposed to be delta HR?
Did I lose a delta HR? I lost the delta. Yeah, there's delta HR. I pulled it out of the integral, and then I seem to have lost it, but now we found it again. It reappeared. It was hiding. Okay, so let's see if we can draw some conclusions from all this algebra. Remember, we did all this algebra to understand, remember why we did all this. We did all this to understand how equilibrium affects the reactions involved, in particular how equilibrium affects the maximum conversion I can attain. If you remember, we always like to think, particularly in terms of irreversible reactions, that when I crank up the temperature, I heat things up, then the reactions speed up. Usually we think that's a good thing. Now, if I have reversible reactions, however, I not only speed up the forward reaction when I crank up the temperature, I also speed up the reverse reaction. So it's not clear that the net reaction is going to be better, because equilibrium may limit, I might get to equilibrium faster, but that equilibrium may be less favorable in terms of the amount of product I have versus the amount of reactant I have. So that's why we did all this. Let's see what conclusions we can draw about, or some basic conclusions we could draw about equilibrium. The first thing, the first conclusion is that there's some conclusion. The first thing is that the equilibrium constant, Ka, is a function of T only. So all sorts of things like pressure, amount of inerts, etc., all those things don't affect Ka of T, but they may affect things like Kc or Kx. But they don't affect Ka. So if I know these simple relations, I should be able to infer what the effect of all these other changes would be on the K I usually work with, Kc or Kx. But because I know that Ka only depends on T, so if I keep T fixed, Ka won't change. But if I change the total pressure, change the total volume, change the amount of inerts, Kc may change, Kx may change, and from these equations I should be able to figure out how they change. And we'll do that in a couple of minutes. Next conclusion that we can draw is that Xa, where A is a reactant, Xa, the fractional conversion, comes from the moles of A, Na over the volume. Well, moles of Na and volume are not Ka of T, they're either Kc or K written in terms of capital N, which I should also write here. So they're going to have all these other thermodynamic factors coming in. So Xa, my equilibrium might be a function of everything. If K is much greater than 1, what does that tell me? If K equilibrium is much greater than 1, that tells me that the numerator is a lot bigger than the denominator. Well, the numerator has to do with the product side. The denominator has to do with the reactant side. And all the stoichiometric coefficients are non-negative. So it's product stuff divided by reactant stuff. If it's much greater than 1, that tells me I have a lot more product than I have reactant at equilibrium. So that says the reaction is pretty close to irreversible. How about K much less than 1? If I have K much less than 1, then someone follow that logic the other way. Almost no product. So what does that mean about the reaction? Doesn't go. I mix the reactants together, and equilibrium is hardly any different from what I started with. Well, from Van Hoff's equation, look at this equation. If delta H is positive, then as I raise the temperature, if delta H is positive, d dt of log Ka is positive. So if I have an endothermic reaction, raising the temperature raises Ka. An endothermic reaction means raising the temperature implies Ka goes up. Well, does it really mean that? Yeah, it means Ka goes up. Raising the temperature means Ka goes up. The log of Ka goes up because the derivative is positive. Okay, so what does that mean? That means I get more product or less product?
Less product.
And a 50-50 chance. Get more product because Ka went up. So if I have an endothermic reaction, raising the temperature means I drive the reaction towards the product side. Yes?
But isn't Ka also a function of the composition? Because
No,
if I remember
Ka
well-
is only a function of temperature.
Yeah, but if I remember well, according to the Chatelier principle, if you
Where did Le Chatelier's principle come from? The air? We're deriving Le Chatelier's principle now.
But if you take some of the reactant, then you okay, I see now.
Don't you like that instant where everything becomes clear? You're in a fog and all of a sudden it clears up. We're deriving Le Chatelier's principle. In fact, this is part of Le Chatelier's principle. When if I have an endothermic reaction, I raise the temperature, then the reaction is driven towards the product side. Well, remember, if I have an endothermic reaction, what we think that means, we like to think about that, is that as the reaction proceeds, it sucks up heat. So if I raise the temperature, I drive it in the direction that sucks up the heat because the temperature is higher. So this is the fact of the Chatelier's principle. Audience plan. Okay, how about delta HR negative? An exothermic reaction. If I have an exothermic reaction, what that means is just the opposite. It means the temperature goes up, Ka goes down. Less product. That's Le Chatelier's principle. If it's exothermic, then it gives off heat. So when I heat up the reaction mixture, I make less product because making product would give off even more heat. So it pushes the reaction towards the reactants. So these two together are what we frequently call Le Chatelier's principle. Which in high school said if you stress a system in equilibrium, you shift the equilibrium in a direction that relieves the stress. Right? So that's what this is saying. You heat it up, it goes to the side that sucks up that heat and gets rid of it. If it's an endothermic reaction, that means it goes forward. If it's an exothermic reaction, it means it goes backwards. Okay? Yep.
The Chatelier's principle applies to all the changes to the system, not only the temperature.
We just started. Give me a chance. I'm getting there. Okay. So, anyway, let's, as we said, CI was NI over V. So I would like to also write a K in terms with N's here. So CI is NI over V. So log CI is log NI minus log V. So that tells me that this thing would be equal to K written in terms of N's, and then I've got minus log V, minus sigma alpha I, V to I minus alpha I log V. So that's V to the delta N. It's over, so V to the delta N. Okay, so let's look at some of these other things. How about if I raise the pressure? Okay, if the pressure goes up, okay, remember, I keep the temperature fixed. So this stays the same. So if the pressure goes up, and let's say delta N is positive, then Kx has to go up. I'm sorry. If this goes up, then Kx has to go down. So if the pressure goes up, Kx has to go down if delta N is positive. So if Kx goes down, that means I have less product. So means if delta N is positive, then less product. And similarly, the opposite. And that again is Le Chatelier's principle. If I increase the pressure and the reaction increases the number of moles, then I get less reaction. The equilibrium shifts to the side with fewer moles if I increase the pressure. So if P goes down, etc., or if delta N is negative, it's all consistent. How about if I increase the amount of inerts? So if I add some inerts to the system. If I increase inerts, what happens there? If I increase the amount of inerts, then I increase the volume. If I increase the volume, let's see what happens. If delta N is positive, then I have to increase Kn. So that means I get more products. So I increase inerts, I get more products. See if that one, if I did that one right. I think that went backwards. Well, let's see. Or maybe not. Okay, if I increase inerts and delta N is positive, then I get more products. Just let's see if that's right. Oh, actually, no. If I
Yes, if you increase inerts in the system, wouldn't you be increasing the pressure?
well, it depends how you increase the inerts. You can either increase the pressure, or you can increase the volume. One or the other. Depends how you do it. So it all depends how you increase the inerts. But let's see exactly. So we said that increasing the pressure means less products if delta N is positive. Yeah. Okay, so the way I want to look at increasing inerts, let's see, is so the way I'm looking at increasing inerts is here I'm increasing inerts at constant pressure. So what I'm doing is I'm increasing the volume. So V is going up. I'm increasing the volume. That was what I looked at over here. So it all depends how you increase inerts. If I were increasing inerts at constant volume, then I'd just be increasing the pressure. I know that answer already. So here I'm looking at increasing inerts at constant pressure, so I increase the volume. So it's a different situation. So what's going on here? If I increase the volume, then what I'm doing is I'm decreasing the concentrations overall. decreasing concentrations, I'm diluting the concentrations of reactants and products. So, so if I'm diluting the system, then the side that produces more moles is going to get favored to try to concentrate it. So that's basically what's going on here. It all depends how you do introduce your inerts. So all of these together are Le Chatelier's principle. And you could probably go on and find some other things to change the system. But the effect of temperature, pressure, and inerts all are such that they that the system shifts its equilibrium to try to relieve the effect of the stress. Any questions? Okay, so once we have these notions from thermodynamics, we can go back to reaction engineering, because of course we like reaction engineering much more than we like thermodynamics. Okay, so how would we go about doing design now that we are experts in some of this thermodynamic stuff? Well, if you remember earlier on in the semester, the way we did design is we had a mass balance, which we gave the name design equation to. The design equation was nothing more than a mass balance. And the design equation involved a rate which was a function of XA and T. But in isothermal systems, T was fixed, so R was just a function of XA. Since RA was a function of XA, we had stuff coming in, stuff going out, we had reaction going on. We could relate XA out to XA in based on doing something with RA, either evaluating it at the outlet or integrating it, but everything was in terms of XA, so we didn't need anything else. If we have non-isothermal systems, then a priori we cannot integrate this the design equation, because as XA changes, T changes, and we don't know that relationship. So we need another equation. What other equation will relate XA and T?
Energy
The heat balance, the energy balance. So from an energy balance, that gives us T as a function of XA, or XA as a function of T. And then I combine that with the design equation, the mass balance, which involves RA as a function of XA T. And when I combine them, so I combine to get RA as a function of XA only. So whereas in isothermal systems, T was fixed, so I had RA as a function of XA explicitly. Now, in non-isothermal systems, I use the energy balance to get T as a function of XA. I convert that to XA as a function of T, and when I plug in, that again gives me RA as a function of XA. And once I have that, then I can solve the mass balance, solve the design equation. So that's the basic technique for trying to do this. Now, I've made it a little simpler than it really is. In practice, you can't solve, in most cases, other than trivial cases, you can't just solve the energy equation and plug in the answer into the design equation. In most cases, you need to know the answer of the energy balance to solve the mass balance equation, and you need to know the answer to the mass balance equation to solve the energy equation. So in general, in the more general cases, you write them both out as differential equations, and you have to integrate them together. You solve them simultaneously, not sequentially. If you're lucky, in some special cases, you can solve one and plug it into the other. And we're going to first consider a couple of those simple cases so you get an idea about how you